Okay. Tutorial number 12. Yeah. This week is for Group B. That is the last week for the IRA for both Group A and Group B. Group A, they finished last week. So Group B, today you finish it. Yeah. Okay, so next time, do you want to come? Or you want it to be online? Online, do your study at home. Okay, so I will send you the link. Okay, so as usual, I will send you the link when I probably do it in my office, and then I will send you the link. Okay, so for the exam, what's the advice? Advice is do all the tutorial problems. Do all the tutorial problems. We cannot create something from nothing. Must be somehow related to what you have learned. But normally we push you a little bit inside. Yeah. So go to the core part of the problem. Yeah. So what you see is something like that. Yeah. So you do it and think a little bit more. So if you walk one step ahead, what will you see? Think about that. Yeah. Then we'll give you a lot of way to prepare your exam. Okay. So let's start our tutorial. I have made the recording. So later on, I will send you the link. Okay. So this is related to you have a graph. You can visit the one from any node. So you have altogether 16 nodes here, right? So actually, you can start from any one of them. They are connected. So in this problem, we want to start from 4. Yeah. So it's up to us, arbitrary. I can change it to 1. I can change it to 16, whatever. Okay. So you have learned 2 so-called traversal algo. One is the BFS. The other one is DFS. Yeah. So we will see some examples in this tutorial. So depth is depth DFS. Yeah, depth first search algo. So this kind of traversal method is hit and run. You go there, you find something, you go. You don't grab so many of them. You just see one, enough, very happy, and go. So this is called DFS. The other one is BFS. We will explore more later. Okay, so you start from. So how do we solve this problem? You have a graph here. So there are 2 ways to represent the connectivity of them, of this actors, all this. One is the matrix, right? Adjacency matrix. Or this one is the adjacency list. So adjacent, here we use the adjacency list here. So based on that, you draw the one. Say for example, from 1 you can go to 2, from 1 you can go to 6, from 1 you can go to 5 in one step. So you do it for every one of them. So go to 2, you can go to 1, you can go to 5, you can go to 7, you can go to 3. So the order actually is not important. But when I organize the adjacency list, I always from a lot decreasing. Yeah. So, but this is also the personal preference. There's no need to do it like that. Anything you see, then you include there. So the order may be from 2, you may start from 3, and then 7, and then 5, lastly 1, also can. But sometimes the problem we will say that, oh yeah, when you do this kind of organizer so long decreasing order or increasing order, whatever. So try to be smart to follow the advice or the hint from the question. Okay, so based on that, we have the adjacency list. So it's a plural because we have many of them. So depending on the number of vertices you have. So the adjacency array here has 16 elements here. Each one of them, what do you see? It's a pointer, right? It's a pointer pointing to an object. Yeah. So the object is the adjacency list. So this is one list, this is the second list, this is the third list, and so on. So a lot of them. Okay, so the question asks you, so the one when you do the DFS is somehow related to a stack. You put the one you visit, you put it in the stack, so you know that this is the sequence you did it. Yeah. So here 4 is there. Okay, so you put it into the stack. Then based on this value, you go to 4, and you see 2 of them. You can go to 3. You can go to 8. You choose one of them. Normally we choose the first one. Otherwise, when you do it, will be so 3, right? So the next one will be 3. So look at it. The next one will be 3. So you look at the order from 4, you go to 3. But this is hit and 1. Once you hit 3, you go. Don't stay there anymore. From 3, go to 3. So you will jump to this 3 here. The ADJ, the element number 3. So it is a pointer, right? The pointer point to 4 of them. 2, 4, 7, 8. You check whether 2 has been visited. Yeah. Whether 2 has been visited. Yeah. So the answer is no, because we have just visit 4 and 3. So we decided to visit 2. So the next one we visit is 2. So you see that the next one is 2. Okay, so hit and 1. So we go lah. We don't go to the subsequent node here, 4, 7, 8. We don't. Once we see 2, we are very happy. We go to 2 lah. We go to 2. The pointer of 2. Then this one will have 5 elements here. So you look at it. 1 is the first one. We have not visited before. So 1 will be here. 1 will be here. So we'll put 1 here. Okay. So once we visit 1, we don't go to visit the others because this is DFS, hit and 1. So we go to the next one is 1. 1 is here, right? 1 is here. You can go to 2, but 2 has been visited. So we don't care. This one, we don't go to put it there. We don't put it there because we have visited before. So we go to the next one. So the next one from 1, we can also go to 5, right? From 1, we can go to 5. And 5 has not been visited before. So we visit. So 5 is there. Okay? 5 is there. 5 is there. So according to our strategy, hit and 1, right? You hit 5, then you go. go to 5 lah. Then you see that 1, is it visited? Yes. 2 visited? Okay, yes, right? But 6 is new, right? 6 is new, so we visit 6. So the next one is 6. So you keep doing like this until you so-called reach all the possible nodes. So those nodes are called reachable. Okay, next 6. 6, you go to 1. No, cannot. 5 has been visited. 7 is new, right? So 7 7. 7. Once you say 7, hit and 1, you go back to 7 So yeah, so you keep on doing that. We have to do the backtracking. Yeah, so be careful. 2, you go to 2, visited already. 3 has been visited. 6 is there. 8 is new, right? 8 is new. So we go to visit 8. Because from 7, you can go to 8. So the next one is 8 here. Okay. So all these values are stored in the stack. The top is 8, and then below it is 7 and 6 and 5 and so on. So your stack has a lot of elements. So I cannot draw the stack, but you see that the stack actually is this one. This is the top element. This one is below the top element. This one is below 7. This one is below 6, something like that. Okay, go to 8. Hit and 1. So you go to 8. And then you see 3. But 3 has been visited. We don't use it. So how about 4? 4 has been visited. And then 7 has been visited. But 12 is new, right? So we go to visit 12. Once you go to 12, you see that 8 can go to 8, but he has been visited before. So 11 is new, right? So go to 11. From 11, you can go to 7. Go to 12. No, both of them you have visited before. But 14 is new. 14 is new, so you should go to 14. 14, you can go to 10. 10 is new, right? So 10. From 10, you can go to 6. But has been visited before. 9 is new. 9 is new. Okay, from 9, you can go to 5. Visited before. 10 has been visited before. 13 is new, right? 13 is new, I think. So 13, we go to visit 13. 13. From 13, careful, careful here. 13, first you go to 9, right? And then you visit 10. But both of them have been visited. So what should we do? What should we do? We see that the stack 13 has used up. So actually we can pop it and see the top element become 9, right? So this is how we go back. First, okay, let me demonstrate one more time. So this is 13. So we are supposed to go to 13, check the pointer. The pointer point to the first node. The data part is 9. But 9 has been somehow here, right? Visited before. Then we know that 13, you can also go to 10. So this is the second data value of the node. Okay, so 10 is there. So we have visited these two before. We cannot visit them. So we have to go back. But go back, which one do we choose? So many of them we have visited. So you should go to see that this is 13 you have visited because you have the stack. You know that you pop this one. Now 9 is at the top. 9 is at the top. So you will go back to 9. Okay. So 5 visited before. 10 visited before. 13 also visited before. So that means no way out. So 9 does not give you anything. You pop it up. Then you go to 10. you go to 10. Once you go to 10, you go to 6, visited before, 9, visited before, 13, visited before, 14 is new, right? 14 is new. So now you have to visit 14. Okay, so this is a little bit tricky. So how come I know how to do it? Because we store all the values in the stack. So when we pop it and then we see the top every time. Okay, so now 14 is there. 14, okay, 14. Let me see. So I made the wrong decision. Let me see. 10. Is it 10? 9. 9 is 5, 13. Then we go to visit 10. 14 has been visited. Sorry. 14 has been visited. 6 has been visited. 9 has been visited. 13 visited. 14 also visited. Yeah. So this 10 does not give us any good things. So I go back first. So now we pop it and get the top element 14. So this time is correct. I make the wrong observation. Yeah. So 14 is here. From 14, you see that the first one is 10, then 11 visited before. 15 is new. So you see that you keep doing that backtracking until you see this guy. 15 is new, right? So you use it. The next one, 15. 15 is 6. Visit before. 11 also visit before. Old friends, right? So 14 visit before. 16 is new. 16 is new. So you keep doing that until you have all the nodes, right? So let me see. 2, 4, 6, 8, 10, 12, 16 already. Then we have visited all the 16. So I also demonstrate how I make the mistake, right? But you know what I mean. Okay or not? Any question about this? So you hit and one. So this is a basic strategy. But once you see that the whole adjacency list, all the nodes you have visited, then you because you have the stack, so you pop the first guy, the top guy, and see the one below it. Yeah. Then you keep doing that until you find the new one, right? Okay or not? Online students, yeah. So okay or not? Okay, so I assume that you have seen, you know what to do. So this time you see that the IRA, you have to find this one. Okay, next one. Next one is the same, but using another strategy, right? It's called BFS. Now BFS is different from DFS. That guy is hit and one. This one is not. This one is like that. You explore all the nearby nodes, as many as possible. Then, once you finish it, you go to explore another one. So the strategy is like that. Yeah. So you see that from NTU, you go to visit Pune, you go to visit Hamanturong, you go to visit class, whatever, the one nearby. Okay, as many as possible. Then once you finish it, say from Pune, you can go to Chinese Garden. Then you go to from Pune, you go to Chinese Garden, you may go to Jurong West, you may go to Jurong East, whatever, from Pune. So this is what we call the BFS. You try to visit the nearby nodes as many as possible. Okay, let's see. you have the adjacency list, the same as before, right? So we also start from 4. 4. The guy 4 is here, right? So we start from 4. The first one is 4, right? So from 4, so this time when you store it, you store it in a queue. You store it in a queue, You store it in a queue. Okay, so once you see 4, you put 4 there, right? So you first one, you visit 4. From 4, you see the linked list has 2 nodes here. The first one is free. The data part is free. The second one, the data part is 8. You go to visit the nearby nodes here, 3 and 8. How about that? 3 and 8. So this is the, let me repeat again. Because 4 has been chosen for you, I can choose any one of the 16 nodes here. So we go to 4. 4 has 2 nearby nodes here, reachable. Reachable. So we will visit all of them, 3 and 8, 3 and 8, 3 and 8. So once 3 and 8, we are very happy we visit all the nearby nodes, right? So the queue here has 4 elements, 3 elements here. The first one is the head, the fun part of the queue. So we dequeue it. Once we dequeue it, the first one is free. So we'll use free as our next target. Okay, let me repeat again. So you see that in your queue, you have 3 elements. The first one is 4. We start from 4. And then you see that you have 2 nodes nearby. You put them into the queue. So the queue will store this one here. But we have already visited all the neighbor nodes of 4. So we dequeue it. Once we dequeue it, the first element, the fun element, will be free, right? So we'll use free for our next traveling. So we go to free. Once we go to free, you see 2, 4, 7, 8 has visit. So 2 is new, 4 not new, 7. So 2 and 7 are new, right? So we will visit all the neighboring node. So we have 4 of them, but 2 of them are new, 2 and 7. So the next one is 2 and 7. Okay, now 2 and 7. So in this case here, we use up all this number 3, no use at all. So you dequeue it. You can retire. This one retire. Dequeue. Then the next one is 8. The next one is 8. So you see that 8 is there. You go to 8. You look at it. 3 visited before. 4 visited before. 7 visited before. 12 is new, right? So we visit 12 and put it inside the queue. Okay, so since 8, the 8, right, we have visited all the one nearby, 8. So 8 can retire. So we dequeue it. So now you see that who is at the front? 2. Number 2 is at the front. So you see 2. 2, you can see 1. You can see 3. So 1 is new, 3 not new, 5 new, 7 not new, 1 and 5 are new. So we will visit them one by one. So we visit them one by one, 1 and 5. Okay, and put it inside the queue. Then this 2, number 2 retire. Dequeue it. Because we have used up all the information inside it. Then the next one we explore is number 7. Number 7. You look at it. The color is changing, right? So when you do it in the exam, you can put color, but you are not that flexible, you underline it. You underline it. Let me know that. If you have a lot of color pencils, yes, okay. If not, then underline it, circle it, whatever. Give me some hints. What's your thinking? Don't just use the pencil, just do it like that. Cannot see it. Okay, 7. 7 is 2. 2 has visited, right? 3 has been visited. 6. 6 is new. 8, not new lah. 11, new. So 6 and 11 are new, right? So we'll put it inside the queue lah. 6 and 11, right? So do it very slowly, yeah. But I want you to know what I am doing, Okay. So now because 7 retire, so the fun part will be 12, right? 12 is the next one. 8, no use Visit before. 11 visited before. 16 is new, right? 16 is new. So we put 16 there. So inside the queue, 16. Then we go to 16. No, go to 16. Go to 1. Because we are using the queue. The queue, the active element is the fun part of the queue, right? The fun part of the queue is 1. 1. 1, you can go to 2, no use, visit before. 5, no use, visit before. 6, also visit before. Then what should we do? All 3 of them, 2, 5, 6, or all the data part, you see that give you free note. But you have already visited them. Then 1, also no use, right? Retire, or no contribution, but retire. So 1, retire. We queue it. So, but we don't have new adding there. No new one there. So now we go to explore 5. Now 5 is here. 1, 2, 6. 1, 2, 6. 6 is there. 9. 9 is new, right? So we get some new guy here. 9. So in this case here, 6, 5 retire, and then 6 will be the number is the fun element. So you go to 6, 1, 5, 1, 5, no. 7 also visit before. 10 is new. 15 is new. So these 2 guys are new. So the note 10, the note 11 should be added to the queue. To the queue lah. This one. To the queue. So in this case here, 6 retire. 6 retire, right? We queue it. Now we go to 11. We go to 11. When we go to 11, you look at it, you have 7. 7 visit before. 12 visit before. 14 is new, right? 15 is not new, you visit before. 14 is a new guy here. 14. 14. So let me see how many. 2, 4, 6, 8, 10, 11. One more. Okay, so now 14 has been added. We go to 16. 16 is 12. 12 visit before. 15 visit before. So no contribution, but we retire it. 16. You go to 9 because we need 1 more in order to visit all of them. So 5 visit before. 10. 10. Visit before. 13. Hey, 13 is new, right? 13 is new. So the next one should be 13. Once we go to 13, you see that you have done all of them. You have visited all the notes, 16 of them. Then you can also retire. No need to carry on. So this is the one. So any questions how we do it? Yeah, so you have to do it. So not difficult, but sometimes we have to be a little bit tedious, yeah, because we are not computer, right? Computer can do it very accurate, yeah, but it's very dumb lah. So you have to teach the guy, the computer to do it. Okay or not? Online student, any comment on that? We have demonstrated both methods, BFS and the DFS, right? So BFS, we are using the queue to do it. The previous example, DFS, we use the stack. So you see that the stack and queue will come back again and again. Yeah, so useful, huh? Okay, okay or not? Done now? Any questions? Yeah. Or we are too slow? So actually I can do it very fast, yeah. But I think this is what my style, always try to be easier for you. Okay, so this one is like that. Don't read this one. Don't read the proof. So basically, you have two trees, spanning trees. You have a graph. From the graph, you get the spanning trees. The graph, then you get the tree. The tree is a tree. You see the spanning tree is a tree. And also it contains all the nodes of the graph. Then that one is called the spanning tree. Okay or not? This one. You have a graph, very complicated. Okay. But you see that you can form a tree. A tree is different from that. You have a tree. From the tree, you keep all the nodes of that graph. If the graph has 16 nodes, like our previous example, your spanning tree should also have 16 nodes. Yeah, here. How to connect them together is different. Yeah. So spanning tree. Now suppose you have two trees here. One is called T, the other one called T pi. Suppose let's see the example first, line by line. Now, so you see that this is a graph. G is a graph. You look at it, G is a graph. From the graph, we can form the spanning tree. Then the tree, you know that no loop, no loops. Yeah. So here, you can see that all the nodes here is here. This one is here. This one is here. This one is here. This one is here, and so on. You see that all the nodes, all the vertices are kept. So they are linked together. So this one will be the spanning tree. The spanning tree. There are two spanning trees here. So this is another one. This is another one. So you compare this one and this one. The red one also have all the nodes. All the nodes here. Okay, so this one is the spanning tree of them. Okay, suppose that an HE is in T, but not in T pi. So what does it mean? So now you have this guy called E. E is an H. Joining these two here. Joining these two here. Right? So this one is in T, but not in T pi. T pi, you don't see this one. You don't see this one. And also you observe that in T pi, you have a E pi, this H here, but in here, you don't have. These two are highlighted because they link these two components together. So this one is one component. This one is another component. Component is they are self-connected, but this component has no link to this one. Because this one is a spanning tree, you remove this one here, then you will see two components. Similarly, you remove this one here, you will see two components. There are two components. Okay, so now you see that you have two components. If you want to join them together, how do they join them together? Oh, because you have the E prime here, right? In the red one. Can we use the E prime here? Once you put the E prime here, then this one is linked together, and this one is a spanning tree, right? This one becomes a spanning tree. And similarly, so you look at it, you have two components. How come they are two components? Because they are not linked together. But you see that if you have a E, you put it there, link them together, you borrow from it and exchange it with that, then this one is also a spanning tree. So this one, now you have better understanding of that. Okay, let's go back. So first we have two spanning trees. They are connected of a connected graph G. So suppose that in T you have the E, but not in T prime. So that if so another one is E prime, so you know that. So this one is a little bit advanced. What does it mean? T minus E. So you have a T, you subtract E from it. So it's a difference of set. You have learned that before. You have learned that before at the very beginning, right? The difference of two sets. So you have T, you subtract, you remove this particular element, particular set here. That means you remove that particular edge. You add another one. This one is cup. This one is cup. It's a cup. It's a cup. So it's a union set. So this one is E prime, another one. So that means you remove this one and add another one E prime here. This one is a spanning tree. And similarly, this one is also a spanning tree, right? You have T prime, you remove this E prime, but you add the E to it. So this one becomes a spanning tree. So the explanation is like this. Suppose graph G is a general, has two spanning tree. One is called T, the other one called T prime, right? Then we observe that E in T, but not in T prime. If we remove this guy, the E from T, so because it's a spanning tree, so you join all the nodes together, right? So if you take out one, they will be broken into two separate components. We call it T1 and T2. So you observe that how come in T prime they can do it? Because they have E prime. So if we add the E prime to it, we get a new spanning tree. The spanning tree is the T, you remove the edge E, but you add back another one called E prime here. Then this one is a spanning tree. And similarly for the others. So you look at it. First, you have the tree, you have the graph. From the graph, you have two trees. One is called T, the other one called T prime. Because the spanning tree is very use minimum edges here to connect them together. So you see that if you remove one of them, surely they will be broken into two pieces. Each one is called a component, right? So this component is separate this component, and the same situation also applied to the T pi. But you observe that how come they can connect together? Because you have the E here, E pi here. So if we use the E pi to connect these two components together, then this one is connected, and it must be a spanning tree. You can go to anywhere you like with all these connection here. And similarly for the red one, so is the T pi. So you think about that, yeah. So this one explanation is not easy, but the diagram is easier to understand. So any comments on that from the online students and also from the in-class students? So you have to, I think the most difficult part is the set notation here. So you remove this H from T, you remove it, you remove the HE from T, right? Then you add back. So you use, because they are sets, so you use the union, use the intersection, this kind of set operation here. So the difference of two sets here, this T is a tree, is a set, and this H is also a set here. So you remove it from that, so this one will become a smaller set, but you add back your N, not N, the union, right? We call it the cup, this one here, E pi. You add this one back to it, then they will join together and become a spanning tree. And similarly for this guy here. Questions? Once you understand the set operation, then this one is not difficult. But you see that, how come you have minus something? This one minus, you cannot use your calculator, right? It's a set operations. Okay, we move on to our last question. Okay, write a stack-based non-recursive algo implementation of depth first search using this approach. A recursive algo. So actually you have seen that in your class slides, right? In your slide. But that one is non-recursive. So you have to do it for recursive. So this one is for DFS. DFS, how do you implement that? You have to use the stack, right? So we go back to review it. Okay, so you see that first of all, we should be given the adjacency list. So from every node, you can go to visit the nearby nodes here. So you know the starting point 4. It can be changed to other values. Okay, so you have to put the 4 into the stack, and also you see that because you have to keep track whether this node has been visited before, so you have to create a counter. to indicate that whether this node has been visited. So initially, then you say that they have not been visited. All 16 nodes here, they have not been visited. Then once you start at 4, 4 will be visited. 4 will be visited. So from 4, you get the pointer. From the pointer, you get the data part of it. So you check whether this one has been visited before. If this one has not been visited, then you quickly put it inside the stack, right? If this one has been visited, what should you do? Then go to the next one, right? Go to the next one, like that. So you keep doing that until you have all of them. So roughly you like that. So you need the adjacency list. You need to have a counter showing whether this node has been visited before. So it's true and false, the value inside, or 1 and 0, whatever you like. Okay, so you have to tell whether this node has been visited, because you have to keep track of that. Okay, so once we have an idea how to do it, then we can go lah. So go back to look at the problem. Look at the answer. This one is recursive. So I don't see any difference between recursive and non-recursive. Also quite long. Yeah. Okay. First of all, the algo is called DFS, right? So you are given the adjacency list. Is this guy lah? So the adjacency list. So basically this one is the array you have. The array you have. The array elements are pointers, right? This ADJ is an array because it's linked to the adjacency list. So every element of that will point to a SLL, single linked list. Okay, so start here is the starting point. So in our previous demonstration, 4 is the start. 4 is the start. Okay or not? Now we'll see the first one. So we have to know how many nodes are there in this ADJ array, right? So we have to call n is equal to ADJ.last. So in our example, we have 16 of them. So we know 16 first. Once we know 16 first, we go to create an indicator whether this node has been visited for every one of them. So visit I. So this one is a for loop here. I is from 1 up to n. You initialize it. They are all false. 16 of them, they are not been visited before. So this one is okay, because you have to keep track of that, whether this one has been visited. So at the very beginning, no, they have not been visited before. Okay, so now we make use of start. The start, because the start 4, right? Yeah, in our example, 4. The 4 node. So this 4 here, visit 4 is true, because we start from there. We assume that we visit this one here. Okay? Okay or not? So what should be next? Once we start it, we have to print this one. Because this one, we have to print this one. We use the print line. So we visit 4, then will be number 4 is there. If the next one we visit number 10, then the next printing will be on the next new line 10 or something like that. You keep doing that, so at the end you print all of them. If you use print instead of print line, then you don't have carriage returner. So in this case, all the sequence will be on one line. Okay, no space. No space. That one. So if the first one is 1, then you is 4. The second one is 10, say like that, for example. Then you'll be 4, 1, 0, and something like that. But we are talking about pin line. So we pin the first one and then the second one on each line. Okay. So now we have to set up the stack, right? I don't do it here. You may use you can call it S. The stack, yeah. So the stack, yeah, S dot stack initial, yeah, bracket, something like that, right? So you know how to create a new stack, right? So here I don't put it there. So I say that we can create that. So you know how to create it, right? One line only. S dot stack initial, yeah. Okay, so S will be created. Okay, so now we will go to visit. We use this one. We put it inside the stack because we are going to start, right? Start. So we should put it inside the stack. So the next one is to push this one into the stack. We push this one into the stack, right? S is the stack. You push it, push the data. The data is start, yeah, because the start is given, right? So we know 4 will be pushed into that. Okay. Based on that, we go to visit all the nodes, the linked list associated with this start. Okay, so we go there lah. So will be a while loop, right? So we go to get the element there, get the pointer there. So we check the stack. The stack at the very beginning we have pushed the start into it, all right? So later on we will push more and more, so we will not be empty in general. So don't worry about that. We have only one inside now. So because later on you visit the node, you will have more node insert into the stack. So you see that whether the stack, then you will go to the linked list to check the first element of that. But the first element, first data element, data part of that should be a node, right? The node, this particular node should not be visited before. Yeah. So we have to ask another question. Yeah. So we use the stack, the top value will be number 4 in our case, right? So we get the pointer ADJ4 will be the pointer, right? So this pointer we call it V. It's a reference. So now we'll check whether this one is null or not. Yeah. If this one is null or not, V is not equal to null. So you have a linked list. Once you have a linked list, you go to visit it, but you visit it, you have to check whether this one has been visited before. So if not visit, yeah, so if V dot data, because how do you get the node value is V dot data. V is the pointer pointing to that particular node. The node has 2 parts. The first part is the data. The second part is the links, the pointer, right? So if this one has not visited before, then you push it into the stack. You push it into the stack. So the stack has more and more elements here, right? So I move this one to somewhere. Okay. So the next one is here. So the visit. So we visit this one, yeah, because this one has not visited. You visit this one, we say that is true, because this one has been visited. we find that this one has not visited, we visit it, yeah. And then we pin line, you pin this data, this particular node we have visit. Then hit and run. How do you run? Break. You break it. You break it. Once you break it, then you end the if part. The if is here. If this node is visited before, what should you do? You have a linked list. The node we are talking about has been visited before. What should we do? Then we have to advance the pointer. V is equal to V next. So we go to the next node here and do this one again and again. So we will try to get the one we have not visited before. And once we find one, we break it. We break it, right? We break it. Yeah. So this is break is new because hit and run, right? We always say that once you hit it, then you run. Okay. So this one is for V not empty, right? This one here. If V is empty, V is pointing to a null. So what we should do, we pop the one here because this one no use at all. You retire it. Yeah, you retire it. Then you end. So this one, this is a non-recursive one, right? Non-recursive algo here. So you have to compare this one with the one in your slides, right? They should be quite similar. So I make it colorful. So you see that like and if is with this if is one pair, right? And while the red one is one pair. And while is and this while is one pair and so on. So I cannot make it one page longer. So I break it into two parts, but I try to make it bigger so you can refer to that. So you can use this one to do your question number 1 and see. But sometimes you overlook is why do we have V dot data? V is a pointer. V is a pointer pointing to a node. Dot data is the data part of this node. Sometimes we overlook that. Yeah. So we say that, oh, we go to this node, yeah, and get the value. Yeah. But actually you go to this node and get the data part of it. Okay or not? So this one is very close to the exam quality. Exam quality. So there are recursive one, non-recursive one. We have the BFS, we have the DFS, right? So many possibilities. But you have to know the structure of that. So here, if you know the SLL, so you know what I mean. You see, this one is ADJ is a pointer, right? The array here. So this whole thing is a pointer. So the pointer is S dot top. Yeah. So you get the top value of that, and your ADJ of that. So this one is one of the elements in the ADJ array, and we call it V. So V is a pointer. So if you are, the concept is here, you know what's that? V is a pointer. So any comment on that? In-class student, online student? I also very good today, 10:50. I finished it according to the schedule, right? Okay or not? Okay lah. So think about that. My advice is do the tutorial questions again and go a little bit further. Say for example, if this one is non-recursive, you try to see whether you can do recursive. If this one is DFS, can you do it for BFS? Yeah, something like that. Yes.
Is the exam like 50-50? So 50 algo, 50 not algo.
I don't know. I don't know. Yeah. But if I try to give you some more action type, so our students are very good in that. Yeah. I ask you to sort it. You know how to sort. Yeah.
But the standard for exam would be something like this.
We cannot get rid of this kind of
So 6.
algo part. So I cannot just say that the whole exam paper. Do not ask you to write the pseudocode. Then the chair will not be happy, right? How come you train the student like that? Only can do work, cannot think. So should be balanced.
So you like algo or you like non-algo?
I don't like algo.
You don't like algo, so
I don't like algo, but I cannot avoid it because as the marker, I mark your question. Even half a question will kill me. Right? Last time I do the mathematical induction. Wow, your idea very wonderful. I use almost 6 days to mark 200 scripts, one question only.
then everything just keeps on.
So I try to avoid it if I have a chance.
Everything has.
Okay, thank you very much. Yeah, so do the tutorial. We cannot create something from nothing. Yeah, so the starting point must be there, but you have to walk one step ahead of that. Then you will see the space is huge. It's very great. Yeah, you will see a lot of.
So much of
Okay.
because
Do tutorial. Yes.
just you got. I don't know, like quiz again.
Do tutorial. Okay.
Okay, amen.
Okay, so I end here. So next week we'll do the Zoom and then send you the link. Yeah, because next week is online. Thank you very much. Yeah.
We like.